Hi, my name is Lucy, the Co-President Innovations at NeurotechUofT. What you're about to witness here today is a project that aims at real-time remote monitoring of EEG signals. The goal here is for our student teams to learn, design, and build our own Biosignals board and improve upon the current technology. What happens here is that the brain signals picked up from the electrodes are fed into the MCP3008 chip to convert the analog signal into a digital one. The analog-digital converter is then connected to a Raspberry Pi, which will analyze the signal and send key parameters of interest to a cloud for storage through an internet gateway. The motivation behind using a Raspberry Pi is for its capacity for edge computing, in conjunction with our project NeuroStack, which was submission to the 2019 competition.
Considering the current state of the world, where there is an ongoing pandemic due to the COVID-19 virus, remote telemedicine is a more urgent need than ever. This Biosignals board enables a technology where a patient can be inspected and monitored remotely. The doctors can extract non-invasively the key parameters of interest to detect brain disorders. Here's a demonstration of our progress up until COVID-19, demonstrating that we are able to gather a clear waveform using the MCP3008 analog to digital converter and the Raspberry Pi.
So for our first attempt at designing our headset board, we started with a MCP3008 chip, which operates over an SPI bus, and we hooked that up to a Raspberry Pi 4. I wrote a driver for the MCP3008 that interfaced lab streaming layer directly with the SPI bus calls and allowed multiple channel samples to happen over the interface. We initially started testing this with a voltage divider with a photodiode resistor, and then we moved on to setting up a waveform generator and a scope in the form of the Digilent analog discovery. The Digilent actually runs off the Pi to try to make sure that we have a common ground between the SPI bus and the device reading. Probably unnecessary, but I just wanted to make sure I didn't fry the Pi. I have over here the MCP3008 LSL driver running, and it's currently streaming to just a basic Python plotting, and then we're actually feeding a waveform of 10 Hz with an amplitude of 1 volt, and then I offset it from the common ground since the MCP3008 doesn't actually sample negative values, and we would have some sort of circuit in theory that would handle this, some op-amp setup that would handle this voltage offset. Anyways, you can see that the scope is showing a pretty clean waveform being drawn. It's a bit hard to see since the way this example script works, it just kind of streams the data over time as opposed to giving a fixed waveform. But you can see we're almost getting a clean waveform from the chip. Unfortunately, the only way that is happening right now is that I'm sampling for every single data point that LSL gets. The chip is sampled 10 times in order to clean the data, and it does work. But again, we see some blips in the data, so it's not entirely clean. But this brings into a problem where we need to run the MCP3008 sampling at a much higher rate than the LSL sampling gets. And every single sample requires the Pi to execute a command across the SPI bus to get the chip to respond. And so that poses a challenge because there is a limit in the bottleneck of that SPI bus and how fast we can drive this chip. There's also another challenge with the MCP3008 only has 8 channels, but only if you need to use them in non-common ground mode, you only get 4 channels, meaning that in order to actually get a total of 8 channels, you need 2 MCP3008 chips hooked up. And the Pi does have 2 SPI buses that would allow us to have these devices on separate buses. But ultimately, we kind of realized that this plus a bunch of op-amps would be a large challenge, I guess, is the best way to put it. And there's a reason why multiple boards for BCI use the ADS 1299, which has support for op-amps as well as a different sample rate internally versus the outputted sample rate. So ultimately, we decided to move away from using the MCP3008 as our main processing chip to move on to the ADS 1299.
Without the barriers of the COVID-19 pandemic, we would produce a PCB board for a low noise and reliable design. To better understand how the Biosignal board works and what is required to build it on a PCB, our hardware team utilized the time in quarantine to scale down the project by building a Biosignals board using the ADS 1299 chip, which is the standard for EEG analysis.
Hi, my name is Arthur, and I'm part of the hardware team with the Neurotech Club at UofT. And I was tasked with putting together the analog side of the Biosignals acquisition board that we have internally designed. So just a quick overview of the product. The Biosignals acquisition board is a circuit that we have designed within our team to filter, amplify, and digitize EEG signals acquired in conjunction with our internally designed headset. And essentially, the two main components of the circuit is the ADS 1299 chip, which is used for filtering, amplifying, and digitizing the EEG signals, and the Raspberry Pi, which is meant to actually manipulate the digital signal to transmit, to then be manipulated. So what I've been able to build so far is essentially to put this 64-pin socket onto a perf board so that we could easily prototype our circuit. So the 1299 chip would go in there, and then I would actually put the power section of the circuit within the rest of the circuit here, or within the rest of the perf board, and then the Raspberry Pi would also be attached. The main problem that we've encountered this year is the lack of access to tools and lab facilities. The resources are easily available online. Of course, we need time to design the circuit and everything. But for example, there's information on the 1299 chip that we can use to, for example, design the power section of the board. And there's obviously information on the Raspberry Pi. The main problem has been lack of access to tools and lab facilities. So the way that we have tried to remedy the situation is to buy our own equipment and then ship it to the appropriate person. So in this case, the analog tools that were needed, such as a soldering iron and a reflow station, were sent to me, and I use it to build what I've built so far. But unfortunately, due to COVID and the pandemic, shipping times have been delayed. An essential tool that I needed didn't arrive in time, and so I wasn't able to actually finish putting together the circuit. The other issue is also the decentralization of tools and the fact that not all students within the club and within the team are in the same city and are really not able to meet up together and physically and actually work on everything together. So even though I'm working on the analog side here, we have another team member who's in New York working in the digital side on the Raspberry Pi, and so coordinating this has been difficult. But if we were under normal circumstances, I believe that we would have been able to put it all together. And so a meaningful application of this board would be essentially like the Muse headset, for example. We would be able to actually put a headset on your head. This board would just be the interface between the digital side and the analog side. So it would just be able to take the signals that are being sensed through the headset, amplify it, digitize it, filter it, and then transmit it to then be manipulated in whatever way it needs to be, or be read in whatever way it needs to be.
We had a lot of fun doing this project, and after all, what better way to learn technology than to build it yourself?